Hello everyone, this is Manish from Skillable India. We are going to start the second session of this course, which is the geometric dimensioning and tolerancing. In today's session, we are going to discuss about the 16 fundamental rules of engineering drawings. Okay, so these rules are very important for any engineer who is completed the 3D model and going to make an engineering drawing through which an machinist or a person who is manufacturing that part will be able to manufacture a part precisely. Okay, so that's why these 16 fundamental rules are very necessary. First of all, in geometric dimensioning and tolerancing, GD&T relies on these fundamental rules. Okay, so GD&T basically holds these rules, and I have already told you that ASME Y14.5 2018 standard, whenever these standards are applied, these rules are automatically invoked. Okay, so these rules are automatically applied on that engineering drawing if it is as per the ASME Y14.5 2018 standards. Okay, so it is written over here that these rules automatically applies where ASME Y14.5 2018 standards are applicable. Okay, and these fundamental 16 fundamental rules are connected with a lot of detailings, okay, into the engineering drawing. One by one, all the 16 fundamental rules we are going to discuss. So we are going to start with the first fundamental rule, which is denoted by A. What does this rule says? Each dimension, okay, so each dimension shall have tolerance. Okay, so any dimension which is being given in the engineering drawing always shall have the tolerance. Okay, except some of the exceptions are there. So except dimensions identified as reference dimension, maximum size dimension, minimum size dimension, or stock. Okay, so stock is also known as the commercial stock size. Okay, so I will be letting you know that what is this commercial stock size means. Okay, tolerance may be applied directly to the dimension. Okay, so we can apply directly tolerance to the dimension onto the engineering drawing or through a general note. Okay, so in engineering drawing, you can write it down through a general note or through the title block. Okay, so here you can see in this example, you can see that this is a title block. Okay, so this is called the title block into engineering drawing, and these are the some tolerances which are applicable on all the dimensions of the drawing. Okay, so these you can see plus minus 0.5 this dimension and plus minus 5 degree. Okay, so these both tolerances are applied on whole engineering drawing. Okay, so that's why this is very, very important. So what does first rule says? That each dimension shall have tolerance except the reference dimension, maximum size dimension, and minimum size dimension. Now the question arises that what is standard stock size? Okay, so basically the stock sizes those geometries are already controlled by established industrial or government standards. Okay, so you can see over here that items, what are the items in this? You can see that angles are there, tubes are there, or maybe rectangular tubes are there, or square tubes are there. Okay, or circular tubes are there. Okay, I sections, C section. Okay, so all these are the standard stock size. Okay, and in India, there is one organization which is called the BIS. Okay, so in India, there is a BIS which controls all the standards behind these shapes. Okay, so in case of bars, sheets, okay, so there are many gauges available. Let's say if I am talking about 16 gauge sheet, okay, so 16 gauge means 1.6 mm. Okay, if I convert this gauge into an mm, so 16 gauge means 1.6 mm. If I am talking about 18 gauge sheet, it means about 1.2 mm sheet thickness. Okay, so this is basically the thickness of the sheet. Okay, so these are some standards which are governed by the BIS of a government, which is a government organization in India. Okay, so these are some standards which are applied all over India. Okay, so these are some strength. That's why we don't have to provide the tolerances in such shapes. Okay, with the help of example, I will let you know. Okay, so in this example, you can see this is a channel section. Okay, so all the dimensions, whether it's a D, this is dimension B, or it's a B dimension or any other dimension. Let's say this is a D thickness. Okay, so this is another D thickness, R2, radius 2, radius 1. Okay, so what's the distance between this? So all these, here you can see MC75. Okay, if I am talking about MC75 channel section, so this is medium weight channel. Okay, so this is medium weight channel, which is a MC75. So whenever we are talking about MC75, so these are the weight. Okay, so this is the mass of the MC75. This is the sectional area. This is the D, which is the size, 75 mm. So in this case, 75 mm is the size of this D. 40 mm is the B. So this size is called B is equal to 45 mm. Okay, so these are all the standard. Okay, so MC75 have all the standard, in the table. Okay, so these are applicable all around India. Okay, so you can see all the things inside this table. Okay, so this is called the standard stock size. Okay, or the commercial stock size. Okay, so generally we use this word commercial stock size rather than stock size. Okay, so this is the example for that. So what does this second fundamental rule says? That dimensions and tolerancing shall be completed. Okay, so whenever on an engineering drawing, if you are making an engineering drawing, so first thing you must see that whatever dimensions you have provided, they are enough to manufacture that part. Okay, dimensions and tolerances. Okay, so both the things you have provided onto the engineering drawing shall be completed. Okay, so there is full definition of each part feature. Okay, so there is not any ambiguity or any confusions or any assumptions for the machinist or a person who is reading that drawing. Okay, so the drawing should always be completed in the in terms of dimensions and tolerances. Okay, if there is any ambiguity or assumptions, so what is not allowed in as per the ASME Y14.5 2018 standard in the 60 fundamental rules, that a person cannot scale a drawing or make an assumptions on the basis of other dimensions. Okay, so sometimes on a soft floor, what happens that if our design engineer has missed some dimensions onto the engineering drawing, so the person who is there onto the machine who is manufacturing the part, he makes the use of engineering scale and scale the dimensions into the engineering drawing. So it is strictly prohibited that you should not use this method. So always sometimes in the title block, in this case you can see in this title block, it is written over here that do not scale the drawing. Okay, so these type of points are written onto the into the title block, that we do not we don't have permission to scale the drawing. Okay, so the assumptions are not required. So whenever these conditions are there, we do not have to scale the drawing or make an assumptions. Okay, so this is the second fundamental rule. So what does the next rule says? That each necessary dimension of an end product shall be shown. Okay, so the end dimensions, okay, of any product should be shown onto the engineering drawing. Okay, so in this case, let's say this is the part drawing. So in this case, 60 mm and 30 mm are the end product dimensions. Okay, so the whole outer dimensions of the any drawing or any part should be available onto the engineering drawing. Okay, so this is the necessary. Secondly, this rule says that use of reference dimensions should be minimized. In this case, you can see that the dimension which is written in parenthesis, which is 20 mm here. So we have to try to minimize the use of reference dimension. Okay. In further sessions, I will tell you that why we use these reference dimension and why this rule is saying that we have to minimize the use of reference dimensions. Okay. So we have to try that the reference dimension cannot be used in the established part requirement. Okay. So we have to try to minimize or do not have to use the reference dimension in the engineering drawing. So what does this next rule, D rule, says? That dimensions shall be selected and arranged to suit the function and mating relationship. Okay. Mating relationship of a part shall not be subject to more than one interpretation. Okay. So what does this mean? That whenever we are putting dimensions onto the part drawing, okay, into the engineering drawing, what we are making, okay, so there should not be more than one interpretation for the same drawing. Okay, so in this case, in this example, you can see that we have selected and arranged dimension in such a way that the part feature, you can say that the part feature and the function and their relationship, okay, in this particular case with each other should have correct interpretation. Okay, so in this case, you can see that the line, which is I will say the extension line in this case, as used as the boundary line is used as an extension line, which is not correct. Okay, so we have to give dimension in such a way that that extension lines should be different from the boundary line. Okay, so whatever the part lines should be there in the engineering drawing, we don't have to use as an extension line. Okay, because it will make a confusion, okay, for the machinist. So that's why we don't have to make such practices which are not worthwhile and which makes a lot of confusion. Okay, so in this example, you can see that we are using a part boundary or a surface. These are the surfaces, okay, as an extension line. So there can be misinterpretation, which is not the right thing. Okay, so to eliminate this confusion, what we have to do is, actually this is a simple drawing. Okay, so that's why we are able to read and understand this drawing. But when there is a complicated drawing and we are using a boundary of or a surface as an extension line, it may cause misinterpretations. Okay, so to reduce this difficulty, to reduce this problem, we have to make a separate extension line out of the boundary of the part. Okay, so always remember this, that that we have to give dimensions or on the engineering drawing outside the part boundary using the extension lines. Okay, so maybe like this, we have to give the dimensions. Okay, so these are the extension lines which should be written away from the part. Okay, so this practice is not allowed into this with the help of this rule. Okay, so correct way of showing the dimension is like this. Okay, so this is the rule number D. Now the next rule says, so what does this next rule says? That the drawing should be define the part without specifying the manufacturing method. Okay, so whenever we are creating an engineering drawing, let's say we are creating a part which has a hole. Okay, so we have to define the diameter of the hole but we do not have to define the manufacturing process onto the engineering drawing. Okay. So in this example, you can see that only the diameter of the hole is given without indicating whether it is to be drilled. Let's say this is written over like this: drilling process or wire cut to be done. Okay, so this is not permitted. Okay, so these type of manufacturing processes don't have to be written onto the engineering drawings. Okay, so whether we have to drill a hole or whether we have to create it with the help of EDM or with the help of wire cut processes. Okay, or whether we have to punch a hole. Okay, so we don't have to write onto the engineering drawing. Okay, so this fundamental rule basically specifies that we don't have to write the manufacturing methods onto the engineering drawing. However, in some cases, it is written that, however, where manufacturing, processing, or the quality assurance or any environmental information, if it is essential, then to the definition of engineering requirement, it shall be specified on the drawing. Okay, so sometimes the condition comes that sometimes we have to write it down some points related to the environmental assurance, okay, or the quality assurance. Some environmental informations we have to write it down. Some processings are there. So those important notes we can write it down onto the engineering document. Okay, so it is saying that it shall be specified on the drawing or in the documents. Okay, in this case only, a limited length of the area of a surface is to receive additional treatment. Okay, let's say in this example, only this much area requires the induction hardening. Okay, so this additional treatment or consideration within the limit is specified on the drawing. Okay, so these type of specific processes we have to show onto the specific processes. We have to show onto the engineering drawing. Okay, so these things we can specify. Okay, in this case, you can see that only this area requires the short pin. Okay, so we have to specify this onto the engineering drawing, or we have to require the masking on the plate. So we have to write it down onto the engineering drawing. Okay, so these are the specific special cases for the specific additional treatment of the part. Okay, so these we can specify onto the engineering drawing. Okay, so this is what this rule says. Other than this, these processes like drilling, rimming, wire cut, punching. Okay, so these type of processes we don't have to write onto the engineering drawing basically. Now, what does this next rule says? So in this fundamental rule, which is F, says that non-mandatory processing information. Okay, so what is this non-mandatory processing information shall be identified such as non-mandatory manufacturing data or a reference information like finish allowance or a shrink allowance, etc. Okay, so what does the this actual fundamental rule says? That if we specify the non-manufacturing non-mandatory data, which is the non-mandatory manufacturing data onto the engineering drawing, so we have to specify on that. Okay, so why we have to specify? In some cases, let's say if we are manufacturing the part and we have given some dimension. Okay, let's say we have given some shrink allowance, or let's say a finish allowance. Okay, let's say some hardcore coating has to be done onto the surface of that part. Okay, so we have to manufacture the data by reducing the thickness of the finish, let's say 20 micron or 50 micron. Okay, so we have to reduce into that manufacturing part. Okay, so we need to specify this non-mandatory processing information. Okay, shall be identified such as non-mandatory as in the form of non-mandatory manufacturing data. Okay, so processing dimension that provide finish for finish allowance or shrink allowance. Okay, So provide the final dimensions are given on the drawing. So we need to give the final dimensions onto the drawing. Okay. So the manufacturing part plus the finish. Okay. So this becomes the final dimension. Okay. So whatever the final dimension, we need to specify onto the engineering drawings. So the next fundamental rule says that dimensions should be arranged for optimum readability. Okay, so whenever we are placing the dimensions onto the engineering drawing, let's say we are giving dimension to the part in the engineering drawing, so it should be arranged in an optimum manner that it is easy for the person to read it. Okay, so optimum readability should be there. We have to arrange in such a way that it should be easily readability. Okay, dimensions should be shown in true profile views. Okay, and refer to visible outlines. Okay, so in this particular fundamental rule says that whenever we are giving dimensions to the part, okay, so we have to align in such a manner that in this example you can see that dimension lines should be aligned and grouped for uniform appearance. Okay, so in this you can see that all the dimensions are aligned in such a way that they are grouped and uniform appearance is looking. Okay, so these are uniformly arranged. Okay, so all the extension lines are properly arranged. Okay, if there is need, so we have used this extension line for this dimension and these dimensions also. Okay, so it is aligned properly. Now, if there is a requirement that we need to stagger our dimensions, or alignment should be in the form of staggering. Okay, so we can also stagger it in such a way. Let's say this is the part, this is the second example. So in this example, several parallel dimension lines, the numerals should be staggered for easier reading. Okay, so we have to stagger. If we are staggering also into our engineering drawing, so we don't have to stagger in such a way that the extension lines or the arrow we are denoting the dimension, it is going somewhere else. So it is not the person who is reading the dimensions. It is going to be misinterpreted. Okay, so this is very, very important that the dimensions which we are providing onto the engineering drawing should be aligned properly and it should have the optimum readability. So in this fundamental rule, it says that wire, cable, sheet, rods and other material manufactured to gauge or code numbers, okay, shall be specified by linear dimensions indicating the diameter or thickness. Okay, so we know that there are many things like tubes, like rods, like wire, sheets. Okay, so these are comes in with the gauge number. Okay, let's say if I'm talking about I've already given you this example that if I'm talking about 18 gauge sheet. Okay, so means this gauge I'm in the reference of 1.2 mm thickness. Okay, I am denoting the thickness which is 1.2 mm. Okay, so this is how we provide the thickness, and these standards are throughout. Okay, we are using the wire or we are giving the sheet. Okay, so what does this rule, fundamental rule says that we can specify the gauge onto the engineering drawing, but first of all we have to give the linear dimension for it. Okay, so in this case you can see in this example we have to specify the thickness as a linear dimension. Okay, so as a linear dimension we have to provide the thickness, then only we can use the gauge. Okay, let's say if I want to specify the gauge also, so I can specify the 20 gauge over here. Okay, so as this rule says that we have to specify the linear dimensions onto the engineering drawing, then only in bracket or we can show the gauge or the code number. Okay, so the gauge or code number may be shown in parenthesis. Okay, so whatever parenthesis we can use after the linear dimension following the dimension. Okay, so this rule basically says that after giving the linear dimension we can write it down the gauge or the code number into the parenthesis. So what does this rule says? In this rule, a 90-degree angle applies where the central lines or the lines depicting feature are shown at the right angle. Okay. So in this particular example, if we take as an example, so what is actual rule saying that whenever the part is showing the axis or the center line of that axis, or the axis is shown of the shaft. In this case, this is the axis. This is the axis shown in the shaft. Okay. So whenever the axis or the center line is given, so there is no need to mention the angle which is at 90 degree. Okay. So in this you can see that this is the surface. This is the surface. This is the surface of the shaft. So the surface of the shaft is perpendicular to the axis. Okay. So in this case, this 90 degree, we don't have to show onto the engineering drawing. Okay. So it is already clear that whenever the axis is there, which is perpendicular to the surface, so it means it is already at 90 degree, and we don't need to show the right angle or the 90 degree angle onto the engineering drawing. Okay. So here it is similarly saying that no angular dimensions is specified on a 2D drawing, orthographic drawing. Okay. So there is no need to specify this whenever this case is there. In this second example, you can see that in this part, this hole, this is a hole which is having a center line. Okay. So this hole's axis and the bottom surface is perpendicular to each other. Okay. So in this case, this 90 degree, which is here. Okay. So in this case, there is no need to show onto the orthographic view. Okay. So it is clearly shown that whenever there is an axis which is perpendicular to the surface, so we don't have to specify the 90 degree angle onto the engineering drawing. Now, what does this next rule says? A 90 degree angle applies where the center lines of the feature in a pattern or lines shown at right angle on a 2D orthographic drawing are located and defined with basic dimension is specified. Okay. So in this case, you can see this this hole is having a center line. Okay. So this is the center line over here, and this is the center line over here. Okay. So if I particularly make this center line, okay, so this is the center hole in this, this is the hole. So we don't have to show this 90 degree angle onto the engineering drawing. Okay. So there is no need to show this 90 degree angle as well. Okay. So it is clearly shown that both axes are perpendicular in nature, are perpendicular to each other. Okay. So in this case also, we don't have to show the 90 degree angle onto the engineering drawing. Now, what does this next rule says? So in this rule, what this rule says, the zero basic dimension applies where axis, center planes and surfaces are shown coincident on a drawing. Okay. And geometric tolerances establishes the relationship among the feature and feature of size. Okay. So in this example, you can see in this example that the point where the two surfaces are meeting. So this surfaces have the 0, 0 baseline. Okay. So from here, if we are taking, let's say, if we are taking multiple positions of the geometric tolerances from here for this axis, so these are multiple center lines or axis from the surface. Okay. So this from this 0 point, it is creating multiple, establishing a relationship among the feature. Okay. In this case, feature is a surface. Okay. So the distance between the center of the hole. So in this case, these are multiple holes. Okay. So these are hole center points. Okay. So the distance between from the 0, 0 baseline. Okay. So in this, you can see that we are getting from one feature or feature of size, we are getting multiple dimensions we can take. Okay. So we can apply this 0 basic dimensions whenever we have the center plane, axis or surface, which are coincident in a drawing. Okay. So this is the K rule. So what does this next rule says? This is very important rule in the 16 fundamental rules. Okay. So the rule says unless otherwise specified, all dimensions and tolerances are applicable at 20 degrees Celsius. Okay, so whatever dimensions we are giving into the engineering drawing, okay, those dimensions and tolerances are only applicable where the room temperature is at 20 degrees Celsius or 68 degrees Fahrenheit. Okay, so why this is important? 20 degrees Celsius we need to maintain. Okay, if the temperature is different as per the manufacturing requirement, okay, so whatever dimensions and tolerances we have given into the drawing, and where the part is manufacturing, if the temperature is different other than the 20 degrees centigrade, then especially we have to provide some compensation to be made in the measurement, okay, made to other temperatures. Okay, if we are measuring the same component at other temperature other than the 20 degrees centigrade, then we have to give some compensation. Okay, so why all these things are happening? Okay, and why there is a requirement for the standard rooms in the companies? Okay, so if a company want to take ISO, okay, ISO guidelines, then they have to make a standard rooms into their manufacturing or the measurement areas. Okay, every company is having the standard rooms, either whether they are using that standard room or not, but they are having because they have to fulfill the requirement of the ISO. Okay, so that's why this is the requirement. One of the, I will say in this, one of the basic principles of metrology is that the part dimension changes with temperature. Why this temperature is so important? First of all, I will give you a brief discussion about this. That temperature, according to the temperature, the basic principle of metrology is the part dimension changes with temperature because of thermal expansion or contraction. Okay, so whether the material can expand or the contracted. Okay, so this is the basic principle of metrology, that if the temperature changes, the expansion or the contraction occurs into the material as per there the coefficient of thermal expansion. Okay, CTE value changes, so the all these material expansion and contraction are the happening. Okay, now the question comes, why temperature is so important? Okay, let's say in this case I will give you one example. Okay, suppose there are two mating parts. Okay, suppose there are two mating parts which are going to be assembled with one another. Okay, one is of steel and other is of brass. Okay, what will actually happen? Because as we know, both the values of either it's of a steel or it is of brass. Okay, if both the parts are being manufactured at 0 degrees Celsius. Okay, let's say the condition is both parts are manufactured at 0 degrees Celsius, steel part and the brass part. Okay, now let's say we are manufacturing this part and we need to assemble one part with the other, and material is different, one is of steel and the other is brass. Okay, so when we go on to soft floor, temperature is at 0 degrees Celsius, then time we have manufactured the part. Okay, we know that the CTE value of steel is this. Okay, 12 into 10. This is the CTE value of steel, and brass is about this. Okay, so you know that brass and DC both have different CTE values. Okay, brass is having the more CTE value. Brass is having more CTE value. Okay, CTE is basically a CTE is here is coefficient of thermal expansion. Okay, do not get confused. Coefficient of thermal expansion. Okay, so when we assemble both the part at room temperature, okay, so brass has a more CTE value. So what will happen with the brass is it will get expand. Okay, because it is having more CTE value, it will expand and contract more. Okay, with the change in temperature. Okay, so as it is having more CTE value, it will get expand or contracted more when the temperature changes. Okay, we can face problem at the time of assembly. At the time of assembly, it can be happen that the part did not get assembled with one another. Okay, so this is very important that we need to maintain this temperature, that it do not get contracted or expand in such a way that it cannot get assembled with one another. Okay, since parts are assembled at room temperature, it would seem practical to have the part length measurement refer to the assembly temperature as closely as possible. Okay, so this is very important. It will expand more than the steel part, and assembly may not be possible. Okay, so this is why we need to see and we need to give such tolerances in such a way that the parts get assembled with each other, and we need to as a design engineer or as a production engineer or quality engineer, before if we are checking the part, so we have to keep in our mind all those things that these can if the part is manufactured correctly, okay, then also the condition can come where it cannot get assembled. Okay, so all the scenarios as an engineer we need to keep in mind. Okay, so this is this L rule says this. Okay, now what does this next rule says? So what does this rule says? Unless otherwise specified, all dimensions and tolerances apply in a free state condition. So whatever dimensions we are applying into the engineering drawings, okay, whatever tolerances we are applying to the in the engineering drawings, it is in a free state condition. Okay, now the question occurs that what is this free state condition? Okay, except there is some exception also, except for the non-rigid parts defined with the restraint notes. Okay, so in this two terminologies come out. First is free state condition. Okay, so first we are going to understand about the free state condition, that whatever dimensions and tolerances we are applying into the engineering drawing, it is in a free state condition except for the non-rigid part. Okay, so we are also understanding that how we are giving this to the non-rigid parts, and how we are demonstrate this non-rigid part if it get deformed. Okay, so first of all, what is free state condition? A state where only the force of gravity is applied. Okay, so as you know that when whatever part we are manufacturing, whatever if people are from the quality department, if they are measuring the part, they know that how to apply the pressure onto the whatever mechanism we are using. Either if we are using a micrometer or a CMM probe we are using to measure the part dimensions or the coordinate. Okay, so the minimum pressure we are applying onto the part to measure that part. Okay, so why we are applying the minimum pressure? Because if we will apply more pressure onto the part, it will get deformed. Okay, so because we know that whatever dimensions we have given or tolerances we have given, those in the apply only in the free state condition, and the free state condition is where only the force of gravity is applied. Okay, so where only force of gravity is applied, this is in a free state condition. Okay, so the part which is going to measure onto the gravitational force, whatever part we are measuring, it is going to be onto the gravitational force is going to be applied on that. Okay, as you can see, all the measurements we use, like dial gauge we are using or CMM probe we are using. Okay, so we are applying the minimum pressure get applied onto that part to measure that part. The people who those who are involved in the measurement, they know that they know that they are applying the minimum plunger pressure during the measurements. Okay, so they know that they have to apply the minimum plunger pressure. Even in micrometers, we know that they have the ratchet mechanisms. Okay, if we will apply the more pressure, if we will apply the more required force, minimum required force other than that, it will get free. Okay, so that's why in micrometer we use the ratchet mechanism. That's the apply of the pressure will be not more than the requirement. Okay, so due to which the screw get free into the ratchet mechanism. Okay, so this is why whatever dimensions and tolerances we have given into the engineering drawing, it is according to the free state condition. Okay, now for the exception of the non-rigid part, so first of all, we will understand that what is called the non-rigid part. Non-rigid part basically are the parts like those made up of rubber or resins. Okay, so the parts which are made up of rubber or resin, like it can be O-rings, okay, gaskets. Okay, so these are some of the parts which are made up of rubber and resins. If we want to check the end measurement, because of the deformation, the force of gravity applied onto that. So if we are not applying the more pressure on that, still they can get deformed. Okay, because the rubber can get squeezed if we will not even apply their own weight. Sometimes with the you will see the tire with the own weight, they sometimes get contracted. Okay, so that's why whatever the parts are made up of rubber or resins, so we give some I will say note through the note or through the F symbol. Okay, so we show that this part is in a non-rigid part. Okay, so if we are providing the F symbol onto the engineering drawing, okay, in the feature control frame into the geometric dimensioning and tolerancing, then it is a non-rigid part. So non-rigid part are those parts, those are made up of rubber or resin, where deformation is presumed to acquire due to a release of internal stress generated during the manufacturing process. Okay, if our part is a non-rigid part in which deformation can occur in a free state condition, so there we use the F symbol. Okay, so like this F symbol we use in the feature control frame. Okay, so with the help of example, we will be discussing this. So for parts that deform beyond the size tolerance or geometric tolerance in a free state, F symbol is written. Okay, so in this condition, you can see over here that this is a feature control frame. And in this feature control frame 2.0 F, okay, so this F is showing that part is a non-rigid part. Okay, so F is stand for the free state, okay, which means to apply the tolerance under the free state. Whatever tolerance we are providing under the tolerances under free state. Okay, so this is very important. Okay, so in this example, you can see in any orientation datum, in this datum B must have the roundness. Okay, so this is roundness tolerance of 2 mm. Okay, so this is under the F. F is showing in this part made up of the soft material. So F, if we are applying F into any feature control frame, then the part is made up of soft material. Okay, so this is all about this rule. Now what this rule says. So this rule says, unless otherwise specified, all tolerances apply for the full length, width and depth. Okay, so this is very important, that whatever tolerance we are applying to the part onto the engineering drawing, it is going to be applied on full length, full width and full depth of the feature or the feature of size. Okay, so in this case, let's say D1 is a diameter and M5. Okay, so whatever tolerances we have applied onto the D1 diameter M5. Okay, so in this case, the tolerances which I have applied is applicable onto the full length. Okay, not only this much length, whole length of the part is applied with this tolerance. Okay, so in this the upper size, whatever tolerance we are applying to the D1 diameter, it is applicable to the full length. Okay, in this second example also, in this example, you can see whatever dimension, whatever tolerances we are applying onto the D1-7, it is going to be applied onto the whole depth of this part. Okay, whether it is here, it is here. So it is going to be applicable on each and every part throughout the depth of this part. Okay, so this rule basically applies that whatever tolerances we are applying, it is going to be applied on full length, width and depth. Now this rule says, so in this rule, what this rule says, that dimension and tolerances only apply at the drawing level where they are specified. Okay. A dimension specified on a detailed drawing is not required or applicable at the assembly level drawing. Okay. So what does basically this rule is saying, that whatever dimensions and tolerances we are applying on a part drawing, it is applicable for the part drawing, and what tolerances or we are applying on the assembly drawing, they are applicable only for the assembly drawing. Okay, we cannot use assembly drawing tolerances onto the part drawing tolerances for the part drawing. Okay, because in some cases we see that whatever tolerances we are giving in the assembly drawing, they are little higher than the part drawing. Okay, so whatever part drawing tolerances are there, it is for basically for the manufacturing purpose. Okay, so they are much tighter tolerances, very specific tolerances onto the part drawing. Okay, so this basic rule says that dimensions only applies for a drawing level. Okay, so whether it is for the part drawing, if it is a part drawing, it is only applicable for the part drawing, all the tolerances, and if it is in assembly drawing, it is applicable for the assembly drawing. We cannot mix it up. Okay, let's say bolt, torque, welding, brazing, fresh fit and other assemblies, therefore detailed dimensions do not apply for the assembly level. Okay, sometimes we see that we are using the, I have already told you, very tighter tolerances for the press fit parts. Okay, so whatever they are not applicable onto the assembly level. Okay, at assembly drawing must repeat detailed drawing dimensions when they are to apply in the assembly. Okay, so we don't have to mix it up. This fundamental rules basically saying this. So what does this this rule says, that wherever the coordinate system is shown on a drawing, it shall be right-handed. Okay, so whenever we are showing a coordinate system onto the engineering drawing, it should be always be a right-handed. Okay, what is right-handed? Right hand is basically a positive positive BL of the engineering drawing. Okay, so positive axis we are using into this right hand. Okay, each axis shall be labeled and the positive direction shall be shown. Okay, so basically the positive direction is the right hand direction. Okay, so model coordinate system shall be compliance with the ASME Y14.5-2018. Okay, so this is the standard of the ASME which is provided for the coordinate systems. Okay, so if we are moving towards the positive direction, let's say this is the positive direction or right-handed direction. Okay, this is a negative direction or the left-handed direction. Okay, so whatever time we have seen in the engineering drawings, if you have seen the it is shown in the engineering drawing that if we are using the, let's say, plus 5 BL, plus 6 BL, plus 8 BL, okay, or the it is using the positive direction or the right hand side direction. If we are using the negative BL, like 4 minus 4 BL minus 2 BL, okay, so it is into the left hand or the negative direction. Okay, so this rule says this. Let's take an example that if there is a car and the center point of the car is we are taking as a 0 BL. Okay, so if we see the right hand side door, okay, so the right hand side door is the mirror image of the left hand side door. Okay, so basically the center point of the car is using as a 0 BL. If we are moving towards the right direction, it means we are moving towards the positive direction. Or if we are moving towards the left direction, then we are moving towards the negative direction. Okay, so so this is how we use this fundamental rule, and this is how we can use this into our engineering drawing. So this is all for this 16 fundamental rules. In the next session, we are going to start with another topic. Thank you everyone.